Limits and continuity. So with example one, we're going to do limits with graphs. So taking a look at the graph here, we want to look at limits, and we're going to look at limits at -1 from both the positive and negative side. We're going to look at -2, the value of -2, the limit as x approaches 2 from both sides. So notice that that is a two-sided limit, and the limit as x approaches -4 from one side. Okay, so first one is a one-sided limit. We're approaching -1, and we're going to approach that from the negative side. So as I approach -1 from the negative side, I'm approaching some value here. Yeah, that limit does exist, and it looks like it's equal to about -1/2. Okay, when I look at it from the right-hand side, again, it's continuous through there, so it does have a limit. So as it approaches 1 from the positive side, it equals the exact same point of -1/2. And in fact, f of -1 is equal to -1/2. Looking at the limit as x goes to, sorry, not the limit, but looking at the y value at x equals -2, well, at x equals -2, there looks to be not a point there. Okay, so there is not defined there, so the limit does not exist. So we say D N E does not exist. We're going to look at the limit as x goes to -2, but when we look at the limit now, the limit is different. Okay, so the limit as x approaches -2 is different than the actual value at -2, because the limit doesn't really care what's happening at that point. And as we approach -2 from both sides, from left side and right side, okay, as we approach that from both sides, it's approaching the y value of 1. So what we can say then is the limit as x approaches -2, the limit is equal to y equals 1. And then for the last one, as x approaches -4 from, in this case, the left-hand side, so I'm just going to color code this. So as we approach this from the left-hand side, we're approaching the x value of -4 from this direction. It's headed up. It's going to be heading to positive infinity, so the limit is infinite. In example 2, we're going to look at this graph again. So the limit, this is a graph of f, and for the first part, we're being asked about what's happening on the graph of f. So for A, we're being asked, for part 1, we're being asked which of the statements are false. So looking at statement A, in blue here, we're looking at as x approaches 2, and it's a two-sided limit, does the limit exist? Well, approaching 2 from both sides, I'm approaching 2 from this side and approaching 2 from this side. It looks like it's going to the same point, although the point is not the same as what the limit is. The limit looks like it's equal to 2. That does exist, so that is not a false statement. For B, we're looking at approaching 3 as a two-sided limit. So as we approach 3 as a two-sided limit, it's approaching from the left side, approaching from the right side, and the actual value is 5. So although the limit doesn't really care what the value is, it does have a value, but it does have a limit as well. So it has a two-sided limit approaching 3. So that is not a false statement either. For C, we're approaching 4, but 4 is from both sides. Okay, so we're going to approach x equals 4 from both sides. So although it's not defined from that side, that's okay. There's a limit from the left side. There's the limit from the right side, approaching 4. as it approaches 4 from the left side, it equals 2. Approaches 4 from the right side, it equals 4. But because the two-sided limit doesn't exist, this is definitely a false statement. Taking a look at D, we're going to approach 5 from both sides. So approaching 5 from both sides, that one, the limit does exist, and the point exists as well. So this is not a false statement. And lastly, the limit, the function f is continuous at x equals 3. Well, the limit at x equals 3 exists. So we know that the limit as x approaches 3 from both sides exists. And we also know that it's equal to the f at 3. So it is continuous. So that is not a false statement either. For part 2 of this problem, it says that g prime is equal to f of x. So that f of x function is a derivative function for the function g. And we're being asked which statements are true about the function g. So it says, A says g is differentiable at x equals 2. Well, if g is differentiable, that means that the derivative must be continuous. And at x equals 2, it is discontinuous. So we know that must be false. Okay, so that is not a true statement. So we're not going to consider that as one of our solutions. For B, it says g is continuous at x equals 2. Okay, well, it's not differentiable. It could be continuous, but we can't claim that that's necessarily true. So we're going to say that B is also false. At 2, g is not necessarily continuous. For at x equals 3, we can see that it is, although it's not smooth through there, it changes direction, it's a vertex through there, it is continuous. And so that means then that g must be differentiable because the derivative is continuous at x equals 3. It must be differentiable. So then we're going to say that is a true statement. Okay, I'm just going to color code this a little bit. And that one is true. Okay, so this is one I'm going to circle here as one that I want. And that's what's happening here. It's continuous through that point. Then g must be differentiable. The derivative is continuous, so g must be differentiable. Okay, so for D, this is also true because if it's differentiable at x equals 3, it must also be continuous at that point. Okay, so we're also going to circle that one because that is also a true statement. And for E, we see that x equals 4. At x equals 4, it is discontinuous, so the derivative is discontinuous, but that does not necessarily mean that it is that the g function is discontinuous. We could have a kink at that point. So the derivative, although slope changes abruptly there, we know that it could be continuous because it could just be a kink in that at that point. So we're going to say that g is not necessarily a true statement either.